Hey everyone, continuing with our conics, we arrived at the last graph, the hyperbola. And it's, well, basically two parabolas in the same graph, alright? So the general equation is actually very similar to that of an ellipse, where we have x minus h whole thing square over a square minus y minus k whole thing square over b square equals to 1. Now, in this time round, a can equals to b or a cannot be equals to b, right? It really doesn't matter. Alright, unlike our ellipse. Now, there's also another equation where we just simply switch x with y and y with x. So we have y minus k square whole thing square over b square minus x minus h whole thing square over a square equals to 1 as well. Now, the shape of these two graphs are going to be different. For the first one, let's do this equation 1 and equation 2. The graph of the first equation will look something like this, two parabolas side by side, and this is what we call by a east-west opening hyperbola, right? Then for our y, which is equation 2, it will be a north-south, so it looks something like along the y-axis. All right, so this will be a north-south opening. Now, as one way to remember, basically, if you look at the first variable x, you notice that the two vertexes would lie horizontally, right? So this would indicate that is on the x, being the first one. For the next one, we know that the vertexes will lie on the vertical line. All right, they not necessarily be on the y-axis, but any vertical line, and therefore it's the y being the front one. So that's one way to remember whether it's an east-west opening or a north-south opening. All right, so that will be that. And now we move on to, again, the values of hk and a and b. So hk is still your center, but unlike the center for your circles or your ellipse, this center is basically the center between the vertexes, right? And it's also the center of the hyperbola. And this is also another unique point where it's a center between the vertexes. It's also the point of intersection of the two asymptotes, right? Two oblique asymptotes, all right? So this is also another part of your conics for your hyperbola, more specifically, where there are actually two oblique asymptotes and they intersect at the center, all right? And once again, a and b, well, a would be the distance from your center to the vertex, or depends, for if it's the first graph, it will be the a, for the second graph would be b, all right? Otherwise, then actually the other value doesn't really matter to a certain extent, all right? So that is the idea for your a and b. So in this case, your value of a is the dist from center to vertex, all right, respectively for each equation. Okay, so let's pull out an example, and we'll start with the first equation, all right, where let's say we have x minus, let's say 1 square over, let's say we have let's give us nice square numbers. I'm not in the mood to do anything that's slightly difficult. Y minus 3 square over 9 equals to 1. Of course, if let's say this is ky, then you have to factorize out k and then put it down again. But let's keep it to something that's simple. Alright, so now we know that the center is gonna be at 1, 3. Alright, and we know that a equals to 2. So very simply, our vertexes would be 3, 3 and minus 1, 3, right? Because there are two vertexes and the center is between the center of the two vertexes. Now, the other part is, how do we find the two asymptotes, right? Hyperbola has two asymptotes. Now, because if you look at the graph of this, it will be something like this, right? And you notice that x approaches infinity or negative infinity, then we get the value of y here. It approaches infinity, right? In fact, it actually follows the asymptote something like this, right? So this is a general sketch. So what you notice is that as x approaches infinity, y approaches infinity. So that is the idea. So what we do is, we'll make y the subject. All right, so by doing this. So we will manipulate it until we get y minus 3 whole thing square over 9 equals to x minus 1 whole thing square over 4 minus 1. As y approaches infinity, x approaches infinity, right? So because x approaches infinity, we know that x minus 1 approaches infinity. So this one approaches infinity. Infinity over 4 minus 1 is as good as infinity. Alright, because the minus 1 is now negligible. So we can then move on to the point where, okay, since we have y approaches infinity, x minus 1 whole thing square over 4 approaches infinity, this minus 1 is not negligible, therefore we then find the asymptotes by reducing it to this form. Alright, now I make y the subject, so I'm going to do very fast simplification. Alright, basically taking the square root, considering plus minus, and then bring the minus 3 over to become plus 3. So we then have our asymptotes, one being at y equals to 3 plus 3 over 2 x minus 1, which is simply 3 over 2 x plus 1. We then have the other asymptote, which is 3 minus 3 over 2x plus 3 over 2, which then gives us, let's see, 9 over 2 minus 3 over 2x. Alright, this one will be 3 over 2x plus 3 over 2. Alright, so we know that the center is at 1, 3, so let's denote that center first. So let's say this is 3 and this is 1, our center would be here. Our vertexes, one will be at 1, 3, that will be at minus 1, 3. Sorry, that will be at minus 1, 3, and that will be at 3, 3. So this will be the first of our vertex, then our second of vertex will, let's say, somewhere be around here. Alright, so what I'll do next is I will then draw my asymptotes. Or actually, it doesn't really matter. Yeah, it's better to draw your asymptotes first because your graph need to tend towards that asymptote. So because the asymptotes would then intersect at this lines here, so I'm gonna draw my asymptotes this way. Now, so another thing about asymptotes is that you need to check whether they intersect the x-intercept as well. So you need to find that coordinate. So you have two asymptotes, you have one which is this and one that is this. So this is clearly the one that's dropping down is 9 over 2 minus 3 over 2x because it is a negative gradient here. So this will intersect at x equals to 3. Okay, so this is at 3, 0. You don't really need to actually label this point, but I like to. Then the other asymptote will occur at, well, when y equals to 0, x equals to minus 1. Right, so from here, my other asymptote will go through here, and this will be the positive gradient one. Alright, so we kind of have the asymptote for the graph, and the graph will look very close. So let me just write down the equation of the asymptote, something that you shouldn't forget. So y equals to minus over 2 minus 3 over 2x, then here will be 3 over 2 x plus 3 over 2. We can leave it as 3 over 2, bracket x plus 1. So I'm going to draw the graph now. So I'm going to start by drawing like this. Okay, this is going to be truncated a little. Alright, you want to like make this more like a turning point. Alright, actually let me just try drawing a normal way. Wow, I can draw like a better way. Alright, so your graph looks something like this. It's just that, you know, I don't have a big enough axis. If let's say the y was scaled a bit smaller and one axis is scaled a bit more smaller, you look at like a actual two parabolas, right? But the main idea is that there's a line of symmetry at this point as well. Okay, so that's the whole idea of a hyperbola. So this is a east-west opening one, and the same techniques actually apply to our north-south opening hyperbolas. And the idea is that just like the one for our east-west opening hyperbolas, the distance from the vertex to the center is basically the value of the A for the east-west opening, or B if it's a north-south opening. Alright, so I'll show you the the north-south one in the next video, so do look out for that. Otherwise, this is the first example of a hyperbola where it's an east-west opening one.